Alright gang, here we go. This is for Chem 2 Unit 13. Going to talk about applications of electrochemical cells. Alright, this is it. You've done it. Last video. Nice. Some applications of cells. So this is the last video of a unit. Hopefully you've realized by now, 13 units later, that last video always talks about practical applications. So these are the three main applications that we're going to talk about for applications of electrochemistry. We use them at batteries, prevention of corrosion or rust proofing, and then electrolysis. Okay. Batteries come in two different ways. They can either be defined as primary cells. They can't be recharged, so like your standard AA batteries. When they're used up, they're dead. Gotta go recycle them. Or secondary cells, they can be recharged. So stuff like the lithium batteries in your phone are secondary cells because they can be recharged. All right. Some examples of batteries. We've got lead-acid batteries. These are pretty interesting. These are used when you have to provide a large voltage very quickly. They're also secondary batteries. You can recharge, refresh them. They use solids for the reactants and products. So both the anode and cathode are completely solid. There's no liquid component to them, but they are stuck in sulfuric acid, which can be dangerous. And it's also got a large amount of lead in them. And so like car batteries a lot of times are lead acid batteries. So this is like when your car starts leaking battery acid. This is kind of what you're worried about here. The math for it is really nice because we don't have to worry about our concentrations at all because they're made with solids, so our Q is just equal 1. All right, and so with our Nernst equation, essentially our E cell is just equal to whatever our standard is. So all we really have to worry about is just the anode and the cathode. Alkaline batteries, right? Alkaline means basic. All right, and so these are the most common type of primary batteries: AA, AAA, D, C batteries, so on and so forth. Even those like little button batteries, that you put in like the watch batteries, they kind of look like, little flat discs. So those are alkaline batteries. All right, nickel, cadmium, and nickel hydride, metal hydride batteries. These are the anodes and the cathodes. And then these are really nice because they're pretty lightweight and they provide a lot of voltage for how lightweight they are comparative to like the alkaline batteries and especially the lead acid batteries. Lead acid batteries, because they're made with lead, can be pretty dang heavy, but nickel cadmium and nickel metal hydride batteries are pretty light. Now the cadmium is starting to get phased out using, they don't use those so much because it's toxic and pretty and heavy comparatively, especially against another random metal hydride. And so we don't like when you throw away these nickel cadmium batteries, they can leak into water supplies, and cadmium is really hard to get rid of. And so it's not used as much. So metal hydrides are a lot more common. So like if you're into like RC racing and stuff like that, most of the time you'll use a nickel metal hydride battery in those because they're pretty lightweight, produce quite a bit of voltage in a short amount of time. Lithium ion batteries, these are guys used primarily in electronics. They're a little more expensive, but they can last a long time. They get recharged. They can be recharged a lot, and they produce a lot more consistent and long-term voltage than the nickel-based batteries. All right. I'm trying to talk about a little bit how each of these work. So this is a lead acid battery right here. You've got your anodes and your cathodes, or actually these guys here, and then you notice you've got like an actual space between them where that where you've got this sulfuric acid. They kind of connect from one to the next. Another interesting point is your cathode and your anode here. Notice that they're actually connected directly onto each one like this. And notice here you've got like a little gray piece right here, and so you've got like a little spacer, so you can actually have like individual cells within a battery. It's kind of a way to engineer keeping track of how much energy you're going to put through. So your cathodes are connected here, right, and your anodes are connected here, and then they go through like that, connecting to wherever you want to produce your power out here. With an alkaline battery, you put your anode and your cathode right next to each other, right? So this is our anode, and it's the zinc and the potassium hydroxide. That's where we get that alkaline part, because potassium hydroxide is a base. And then the cathode here, we have this manganese oxide, and it's usually put in graphite or something like that. You put a separator between them so they don't start reacting with each other across here. So the only way they can react is through the top and the bottom and the sides, right? So the electrons can flow around this way. All right, lithium ion batteries are pretty interesting. You just have what you have are on the ends, you have what are called current collectors, and then inside of it, you have an anode and a cathode that are separated by an electrolyte. And so essentially, what happens is on the anode side, you have these carbon rings, graphite, usually. Okay, and you stick lithium in between them. And so these lithium ions are kind of like held in stasis between these graphite rings. And then when you hook this up, what allows to happen is the lithium is more stable when it's stuck in these holes between these layers of this cobalt oxide. So the blue guys there are the cobalt, and then the red is the oxide. And so these lithium atoms can kind of squeeze in there and fill in these holes. So as the lithium goes from one side to the next, it drops in energy. But on this side, you start to gain a positive charge over here, which drags, in order to balance out that charge, it drags the electrons from the current collector on the anode side over to the current collector on the positive side, on the cathode side. And so because this lithium ion is moving, it kind of drags the electrons with it, almost kind of like if you were, if you've ever had like a magnet on top of a piece of on top of a table, and you move that magnet around with a magnet underneath it kind of experience. All right, so that's kind of the general gist of how lithium ion batteries work. All right. And now fuel cells is a different kind of way to produce electrical energy via electrochemistry. But the idea with the fuel cells is, instead of it being a battery, you have to continually provide the fuel to it. Okay, so you don't have this source of energy that's contained in like a little packet. You have to continually provide this fuel. So you have to continually provide this source of energy. And the idea behind this is that it, in theory, is a lot more efficient. And in practicality, it's a lot more efficient. It does have its drawbacks. Like the most common example of a fuel cell is hydrogen fuel cells. And the way it works is you have like a tank of hydrogen out here, and you put hydrogen into a container here, and then you have some sort of separator, and the hydrogen gets oxidized as it goes across here and combines with the water, and or combines with oxygen that comes in from the atmosphere. So on one side of your engine, you've got hydrogen coming in, and the hydrogen goes across, and then you've got your oxygen coming in. And then as the hydrogen ions move from one to the next, you have this electron flow that goes from one to the next, providing power to whatever you needed to provide power to. And then really, so your only waste products is the unreacted hydrogen, which you can really, since it doesn't get mixed with anything, you can just send it back around the loop again. And then oxygen that didn't get reacted, which isn't a big deal because we're surrounded by oxygen, it's kind of handy. And then hydrogen, or water, water, right? H2O. Which is not so bad if we have some extra water bouncing around in the air. All right, so this is nice because we really don't have very much waste for any of these things. All right, and so these protons can migrate across, and then as they migrate across, we end up with this change here. Now, the big drawback is the fact that in order to have a car that runs on a hydrogen fuel cell, you literally have to have a tank of compressed hydrogen in your car, which could be bad if you get in a wreck or something like that. Okay, corrosion. Okay, corrosion is essentially just oxidation, right? Rusting. And so the way this kind of happens is if you have like a piece of iron or whatever it is, or steel that's made out of iron and so on and so forth, you get some water on it, and this water sticks around, and the water essentially allows you to create electric current. It allows the electrons to flow across the iron, and then across the water you can have your cations flow. And so when that occurs, your iron gets oxidized, and it goes from one side, and then gets deposited somewhere else. So your iron starts to get eaten away on the inside of your bulb, little water droplet, and then on the outside of the water droplet you start to collect iron oxide, this brown gunk that's not nearly as strong, not nearly as resilient as the iron is, the normal iron. Okay, and so walking you through, you can walk through yourself through all these steps. It's just essentially we're just showing here the different reactions that can occur as our iron gets oxidized and then our oxygen gets reduced, so on and so forth. All right, so we can prevent corrosion in two main ways. One is using cathodic protection, all right, and then essentially what we're doing is we're just providing a cathode that can react. A lot of times we use zinc, all right, so we coat our metal in zinc, and then it gets oxidized so that the metal is sacrificed instead of the iron that your pipe is made out of. And another way is by actually introducing what's called a sacrificial anode, and the sacrificial anode is attached to the pipe. It has to be attached via an actual connection, and so in order for this to occur, in order for this to work, this anode needs to be more reactive, All right, and so this anode gets oxidized before the pipe gets oxidized. So here's a cathodic protection right here. We've got our iron, but it's being coated by zinc, right? And so the zinc is going to be eaten away and does not produce that zinc oxide like the iron oxide did, right? And so it gets oxidized instead, and so you know, it takes a while to eat through that before you actually get to the iron underneath. So the iron would not be oxidized because it ends up being the cathode by your reaction. All right, and then here with your with a sacrificial anode, here they're using the example of a magnesium anode, which is pretty common. And so you've got this metal pipe underground, and this metal pipe usually made out of iron or something like that, and then you've got, you know, your copper wire connecting your pipe to the sacrificial anode. And so the sacrificial anode, because it's connected to the iron pipe, the magnesium will actually end up being oxidized instead of the iron pipe. So your iron pipe, you know, will last a whole lot longer, and then you might have to go in and replace the sacrificial anode. We also have sacrificial anodes, like in your hot water tank at home probably has a sacrificial anode that might have to get replaced after a while, although the likelihood of your water heater lasting longer than your sacrificial anode is not very high. I'm pretty sure they engineer it that way, so you have to buy a new water heater every once in a while. All right, so here's electrolysis is the last thing that we'll look at here. It's pretty fascinating here. And so what they're doing here, this is the way they make sodium chloride, molten sodium chloride, is you've got here essentially you just got an anode and a cathode and then some mixture of sodium chloride, just regular old sodium chloride. At the anode, your chlorine gets oxidized and loses electrons to form chlorine gas that bubbles up, and then your sodium chloride here, and then at the bottom you'll collect that molten sodium chloride at the bottom just by providing this voltage source. All right, so you're in electrolysis, what you're doing is you're forcing an electron to go in the non-spontaneous path, okay, because normally this would combine, it would go the opposite way. Obviously the sodium is more likely to be oxidized than the chlorine. All right, and then over here they're plating a steel object, you know, with nickel. Okay, so you got your nickel anode, you're applying a voltage source making it go backwards, so the nickel actually gets plated onto the steel. So like when we were looking at that cathodic protection just a second ago, this is a lot of times how they end up coating pipes and so on and so forth with another metal like nickel. All right, and so the nickel actually ends up getting put onto that steel ring, all right, in this particular example. So when you take your, like, if you end up with a you know, say your grandma dies or something, leaves you with a bunch of silverware, you know, and you notice that it's been tarnished, and so because it's tarnished, you know, you scrub it down, you polish it, and some of that silver gets lost, but now it's kind of like looking a little wimpy, you know, maybe your forks are a little skinnier than they used to be, so on and so forth. You can take it to, you know, a place that does silver electrolysis, and they'll stick it into a little bath, and they'll actually run a current through it opposite, and the silver will actually get plated back onto your silverware. All right. And so your electrolysis is really just making non-spontaneous reactions occur, and if you put this outside electricity used to drive the electrons, okay, and so using this electrical energy to create chemical reactions is called electrolysis. Electrolysis and stoichiometry, you know, we put stoichiometry in quotes because it's not really stoichiometry, but it's kind of stoichiometry. Essentially, it's dimensional analysis. All right, so if you just treat these problems as dimensional analysis, you'll probably be pretty good. All right, so treat them as dimensional analysis. So these are some big ideas that you need to keep track of to help you. A coulomb is equal to an amp per second. So if you have a, you know, a current, an amperage, and then a second, you just multiply them together, and that's going to get your coulomb. All right, your coulomb is your charges, okay, and we call that, our book calls it as a capital Q, okay, and our capital Q can also be calculated by our current times our time, which is what we just said, I times T, or our N, our number of electrons, our number of electrons that travel through the wire in a given time times Faraday's constant, 96485. All right, I is your current and amps, T is your time. Your N is different than the Nernst equation N, so beware. Okay, and this N is the number of moles of electrons that travel through the wire in a given amount of time. All right, and then your N is, or your F is your Faraday's constant. All right, and so the stoichiometry, this is just your little roadmap to help you figure out, well, what do I need to do with these units? And essentially, if you just keep track of your dimensional analysis, put what you need to cancel opposite of what you need to start with, and use all your ratios correctly, like these problems aren't terribly difficult. All right, so if you start with quantity of charge in coulombs, you can you can use this to get your current or your time, or any of these three. As long as you have two, you can find the third, right? And then you can use Faraday's constant to convert to moles of electrons. Use your balanced half reaction to convert to moles of your substance that you're looking about, either the oxidized or the reduced, and then you can go from that to figure out your grams. All right, it's not terribly difficult. It's just all about keeping track of your units and canceling what needs to be canceled. All right, so do your practice problems. That's it. Let me know if you have any questions, and I'll see you on the flip side.